Hey everybody, today we're going to be discussing finite and infinite sets with me, and basically all that means is we're going to discuss how many elements are in a set. To start off that discussion, we are going to start with A and B are equivalent. So when they are equivalent, that just means that there exists a bijective function between A and B, and we denote this with a triple equal sign, and when they are not equivalent, we put a slash through that equivalent sign. So to start off, we are looking at A and we are looking at B, and we want to define a function that is bijective between the two in order to determine whether or not they are equivalent. So first thing that I'm going to notice is that we have like this 2, 1, 4, 3. So everything is just offset by 1, which is the case when you're talking about evens versus odds. So if we define a function from A to B, and I'm going to do it by f of x equals x, and then either plus or minus 1. So if I were to try 2, and I do 2 plus 1, that would give me a 3, and so I would have missed this element here in B. And so I'm not going to use plus 1, I'm going to decide minus 1. Now to prove that this is going to be 1-to-1 and onto, since it's a finite set, and it's really quick to just list everything and look at it, it is okay to actually just list it out. Again, this only works because it's finite. So f of 1 is equal to, f of 2 is equal to 1, f of 3, I cannot talk, f of 4 is equal to 3, f of 6 is equal to 5, f of 8 equals 7, f of 10 equals 9. Notice I did not do any sort of like ... crap. That does not fly if you are trying to prove that this is 1-to-1 or onto by listing things out explicitly. You have to list them out explicitly. So I can just say like clearly 1-to-1 and onto, because we can see all of the elements B get mapped to. We can see that none of the elements A go to the same place. So we're good. This is a bijective function. B, or not B, F. F is bijective. So then we can conclude that A is equivalent to B. Now what I want to draw your attention to is like, what if we had had another element in B? Would we have still been able to do a bijective function? And the answer is no. Then we would have had 6 elements over here, and so somebody wouldn't get mapped to, because we can't have like one of these elements splitting off and going multiple places. If we'd had like another element here, then and no 6th element over there, then we would have 6 over here, and then we would have had to have something doubling up and going to the same place. Otherwise, we wouldn't be able to use all of the elements in our domain. So the fact that they had the same number of elements is really important. Which brings us to the notion of cardinality. We say that cardinality for a finite set is just the number of elements in the set. We denote that using like this absolute value symbol, or you could use card of A. Just so you know, your book does this, and that is truly hideous. I don't know what they were on when they decided to write that. Nobody uses that. But let's take this for a quick run. Let's think about the cardinality of A. I can sit here and count these elements. There we go. I have found that they have 5 elements. So we say the cardinality of A is going to be 5. So how is this related to what I said before? Your book does a very convoluted, notationally heavy explanation of this. But what I did was I defined a bijection basically between the set 1, 2, 3, 4, 5 and the set A. And that's really all counting is a bijective function. Congrats! If I were to like try and count the number of spoons that are in my house, if I didn't count one or I missed it, then I wouldn't have counted all the spoons in my house. I would have failed at counting. I've miscounted. That would be the same thing as not having an onto function, because I've missed something. I've missed one of the elements. If I were to accidentally double count one of my spoons, then I would not have a one-to-one function because something has been counted twice. So again, that would be miscounting. So as long as you're counting correctly, that is a bijective function. And so I don't really want you guys to get bogged down in trying to develop bijective functions to count finite sets. If it's finite, you can count it because you have fingers and we're not in preschool anymore. But on that note, you've been dealing with bijective functions since you were in preschool, so congratulations. Moving on, now we can talk about like, what if we start like gluing some finite sets together, like what's going to happen? Part A of this theorem, I think, is very easy to think about. Like if you have A and B are both finite, so like A has 7 elements, B has 3 elements, and they don't overlap, then that's what disjoint means. So A and B don't overlap. Then when you put them all together, you're going to have 10 different elements. And the proof for this is just not insightful. How do you spell insightful? Not insightful. And so we are not going to go over it. It's a trivial concept to think about, but not a trivial thing to prove. And so we're not going to mess around with that. I think you guys get it. Part B, however, this one's kind of fun. So notice when we don't specify the disjointness, so in part B, they're just finite sets, we don't get quite so simple a formula, but it does still make sense like intuitively, because if you have A and you have B and there is some overlap here, then if we count all of A and then we count all of B, we're going to have some overlap. And so we've counted things twice. And so what we have to do is get rid of one of those intersections so that we don't have it showing up twice. So in order to do this, we want to be able to apply this, which means we need to develop a way of writing A union B using disjoint sets. Just by definition of what it means to the difference of sets, remember like A minus B, we could do A like minus B, or A backslash B would be the better notation. So A without B is going to be disjoint from the part where A and B overlap. So union A intersect B. And then to get the rest of the union, we need all of this, all the parts of B that we haven't counted yet. So that would be A union B minus A. So these guys here are disjoint, which means we are now free to try and make use of the first part of our theorem. So let's flip to the next page. We can say that the cardinality of A union B is going to be equal to A minus B plus A intersect B plus the part from B minus A. Okay. Again, because they're disjoint. So that's what? Theorem 5.17a? Cool. Now, what we have is the cardinality for A minus B, but really we wanted the cardinality for like just A. So let's look at our drawing again. This is A. So A is made up of this part. So A is equal to A minus B plus the part that did overlap with B. So it's going to be union A intersect B. Then I don't know, I may have had you prove maybe this one previously, I may have not, but it's a pretty trivial thing to prove, so, or not trivial, but simple thing to prove, so we're not gonna mess around with that right now. we're going to take me at my word. But again, disjoint sets. So now we can talk about the cardinality of A and say it's going to be A minus B plus A intersect B. And now these are all numbers. That's all cardinality is. So we can rearrange this and get information for A minus B. There we go. Now we're going to do the same thing for B minus A. So we could say that B is equal to B minus A union with the intersection. So that would be like, this is B minus A, and then the intersection. Again, disjoint sets. We get to make use of our theorem. And then we're going to solve this for B minus A. Okay, and then I'm going to make room for myself to cite the theorem because I'm proper like that. There we go. Now that we have expressions for B minus A and A minus B, we can go ahead and plug those in from before. So then A union B will be equal to A minus A intersect B plus A intersect B plus B minus A intersect B. So like a more proper way to notate that, star implies. And then we can simplify this. A plus B minus A intersect B, because like these ones canceled out, if you will. And there you go. We have proven our theorem. Whee! And then part C is going to be, remember that's this infinite, or not infinite, this is a bigger union, and you can prove that one by induction. And I've left that one for you to do on your homework. You're welcome. Okay, but moving on. Let's talk about infinity. So there are multiple types of infinity. If I said the natural numbers are infinite, you would probably, hopefully, agree. I could say that the set of integers is infinite. Hopefully, again, you're agreeing. The set of real numbers is infinite. Hopefully, still agreeing. The evens and odds set, if we like split them up, evens versus odds, like they're also infinite. Are these all the same infinity? No, they are not. We say that something is countably infinite if we can write that A is equivalent to N. So if we can establish a bijection between A and the natural numbers, we would say it's countably infinite. Why? Because natural numbers are just like counting. And if we can't do that, we would say that the set is going to be uncountable. So let's look into what it means for, or what other sets are going to be countable. When I first saw this, it kind of like blew my mind. Z is countably infinite, which means we have to be able to establish a bijection with N between Z and N. And I'm just like, but N's a subset. That doesn't work. Oh, my brain. It does work because the infinities are the same size. Let me show you what I mean. So what's a set that is also infinite? The evens. What is a set that is Another set that is also infinite would be the odds. So I can split up the natural numbers into two very separate infinite things. So what I want to do is I'm going to take the natural numbers and I'm going to use the even oddness to split it up. I'm going to say all of my evens can go to positive integers like this, while all of my odds go to everything else. So in this way, you can ensure everything's going to get hit. I've got 1, I've got -1, I've got 0, and then based off how it goes this direction, I'm going to get every single integer out there by counting them using the natural numbers. I think that's pretty cool. This is a piecewise function. I'm going to redefine it real quickly. So we've got x over 2 when x is even. So f is going to be going, by the way, from, what is it? Naturals to z. Yes. By the way, quick fact, we've actually proved this before. If f is a bijective function, then f inverse is a bijective function, and so it doesn't matter which one of these you do. Sometimes it's easier to do one function than the other, just defining wise, and so as long as there's some bijective function between them, it doesn't matter if you go from n to z or from z to n. Whichever one is easier to define is usually going to be perfect. Okay, with that being said, I've decided to go from the natural numbers and into z because I thought it was easy to see, start from the naturals and split up the even odds. Okay, so if I put x over 2, that takes care of this. So yes, can confirm we're just dividing those in half. And then what else? In order to get 1 to map to 0 and 3 to map to -1, I'm going to want -x minus 1 over 2 for odd numbers. Yes, if I plug in 1, I get 0. If I plug in 3, I get -1. That is exactly what I want. Okay, now I feel pretty good about my function, but if we are going to prove that z is countably infinite, I need to establish a bijection, which means I have to justify that this is a bijection. I feel good about it, but we got to prove it. So first off, let's do 1 to 1. So if we have 1 to 1, we say let x and y be elements of the natural numbers, and we want their outputs to be equal. We want to eventually prove that their outputs will also, or their inputs are also equal. So this is going to divide into cases because we've got a piecewise function. Whenever you have a piecewise function, like, be ready to start doing cases. Let's say that the output is positive. If the output is positive for f of x, then since it's equal to f of y, you have that this one is also positive, which means we are coming from the x is even category of x over 2, because all of these guys will be 0 or negative. So then we can say that x over 2 is equal to y over 2, x is equal to y. The other case would be f of x is less than or equal to 0, in which case we would have f of y is also less than or equal to 0 because it is equal to f of x. And so then we plug in this part of the function because that is when the output of f will be less than or equal to 0. And then we know the algebra is going to work. We're going to get that x is going to be equal to y. Okay, so no matter what f of x ends up being, whether it's positive, negative, 0, we get that x is equal to y. So we can conclude at this point, f is 1 to 1. Now let's do onto. Make all of that somewhere. So if we have onto, we want to start with let b be an element of the codomain, which is z. And we want to prove that we're going to be able to find something there. Once again, we're going to do cases. Because here in the codomain, everything got split up into being positive and negatives. Not cases. Case 1. B is going to be positive, then we can say that A equals 2B. So I've defined a variable A, and that would be even. So then if I plug that into our function, since A is even, we would end up in that case for our function. So then there exists A equal to 2B such that f of A is going to be equal to, gonna move it. F of A is equal to f of 2B, which is equal to 2B over 2, which is equal to B. And I got 2B over 2 by plugging 2B again into here because we knew it was even. Okay, that's one case. Second case would be less than or equal to 0. Now we can define a variable A equal to, I'm going to say 2 times negative B plus 1. So A would be an odd number. Right, because negative b would still be an integer because b was an integer. So then there exists A, specifically equal to 2 times negative b plus 1, such that f of A is going to be equal to, let's see, plug this in, 2 negative b plus 1. So we're plugging it in right here. Minus 1 over 2 equals b. I should have left another slide. Did I leave another slide? No, I did not. Okay. Past Gracie did not plan for me. Okay, so we have all the cases. We've covered every possible value of z, and we have found an A that's going to map to them. So therefore, f is onto. So then f is bijective, and that means that z is equivalent to the natural numbers. So then z is countably infinite. So whenever you want to prove something is countably infinite, you develop a function and you make a between n and your set. You prove it's a bijection, and then this is like the template that happens at the end. You're like, then f is going to be a bijection, which means that this is equivalent to the natural numbers, which means whatever it is that you're looking at is countably infinite. So again, this is our template. Remember him, keep him close. So that's what it means to prove something is countably infinite. Let's prove that something is not countably infinite. So different type of infinity. the open interval 0 to 1 is uncountable. Now, hopefully you believe that there are infinitely many numbers in 0 to 1 in that interval, and there are more numbers in there than there are natural numbers, like more. And more in a way, not that Z had more numbers than the natural numbers, because apparently it doesn't, because we can count them all. So let's look at this other type of infinity. In order to prove that this is not countable, so we want to prove this is true, we need to prove that there doesn't exist a bijection between these guys. Going through and listing every single function out there is impossible. We can't do that. And so how do we prove that we can't find one? Contradiction. You suppose that you can. So let's get started with a proof by contradiction. So by contradiction. We're going to suppose that 0 to 1 is countable. We're going to then conclude that since it is countable, then there exists f from the natural numbers to 0, 1, where f is a 1-to-1 onto function. So in order to finish this proof, I'm going to do something that is definitely, this is weird, and it's like a tool that you can put into your bag. I would not expect you to come up with this trick on your own. If math was left to me to discover, trust me, I would not have figured this out. Fun note, or fun fact. Oops. The interval 0 to 1 is all the decimal expansions of the form 0 dot like xxx. I don't like that. 0 dot stuff. So a bunch of digits, but the important part is we have 0 is the number before. So certainly anything that you plug in here, like 3, 3, 3 forever, that's going to end up here in this interval, for example. So now that hopefully you are convinced that everything in here is going to be of the form 0 dot digits, we're going to use that to our advantage. So since it is countable, we have this function, which means I can list this stuff out now. So that means f of 1 is going to be equal to 0 dot, and I'm going to say 1. The first digit is A11, second digit is A12, third digit is A13. And then I can do it again for f of 2. It is also going to have this format of 0 dot and some unknown digits. Then f of 3, 0 dot, a digit, another digit, digits that go forever. And you can do that down to like f of n, but really it goes on forever and ever and ever and ever. But since it's countably infinite, we can list them. That's what it means to be countably infinite. But what I'm going to do now is I am going to take these numbers and I'm going to look at them and say, I'm going to build myself a new number by looking at those numbers. Let's see. So I'm going to define my new function or not my new function, my new number. And it is also going to be a decimal expansion of the form 0 dot some digits that we don't know. But I'm going to pick these digits carefully. I'm going to say that I want to look at all these numbers on the diagonal. And I'm going to say that it's going to be 0 if the diagonal number is not equal to 0. So that means that b of I is going to be different from this number, because if it isn't 0, I've made it 0. But if it is going to be 0, I'm going to say fine, I'm going to change it to be a 1. So no matter which number you look at, it's going to differ by at least one digit, because across the diagonal I have defined b to be I've defined it to be different than everything that we've already listed. So then the problem with this is b is an element of 0 to 1 because it fits this 0 decimal digits business. So it's in there, but f has not mapped to it because it's different than everything that's been mapped to. But f did not map to it. So that means that f isn't onto, because it missed somebody. But that's a contradiction, because f is defined to be a bijection. So basically, what this boils down to is no such f can exist. Since no such f can exist, that means that 0, 1, that interval is not going to be equivalent to the natural numbers, which means that 0, 1 is going to be uncountable. So if 0 to 1 is uncountable, now what we can do is we can use that information going forward. And if you want to prove something is uncountable, if you can say that it's the same as this 0 to 1, like if it's equivalent, develop a bijection between this guy, 0 to 1, and whatever set you think is uncountable, that's how we're going to prove everything is uncountable. So if you want to prove it's countable, develop a bijection for n. If you want to prove it's uncountable, develop a bijection for 0 to 1. Okay. So just to wrap everything up, I want to clarify that countable sets and infinite sets are different things. It's not even that countable is a subset of infinite, because countable sets could mean finite sets, right? We can count the number of elements in a finite set, but you could definitely have a infinite set that is countable, as demonstrated by our countably infinite definition. And then things that are outside of the world of countable sets, those are all going to be uncountable. So if you are talking about a set that is not countable, it has to be infinite. Can't have a finite set that's uncountable. That we can count that stuff. Okay, so with that, I will leave this here and talk to you next time.